Hello everyone. This will be the last video for chapter 3 and it's going to be about calculating using similarity. Now, calculating using similarity is something you've done before, so I'm not going to go too deep into this. Rather, I want to explain why this is so especially useful when working with triangles. Because in the last video, we have seen that for proving that two triangles are similar, we only have to check either the sides or the angles. So that means that we can actually prove that they're similar even if we don't know all the sides. And once we know they're similar, we can calculate the remaining sides. And it's this concept that has been used a lot to do all sorts of measurements where we could otherwise not measure things. In paragraph 3.6, for instance, you'll get an exercise where you use similar triangles to measure how wide a river is, where without that, it's very hard to measure that, because how do you go to the other side of the river? Do you take your measuring tape over by boat or something? That would be difficult. I'm going to do a slightly different example here, but with the very same concepts. And that is of calculating the height of some high tree. So I think I could do like plants here, but I can't actually draw, whatever. So suppose you have this tree and it's hard to measure its height, not in the least because all the branches are in the way. So what you're going to do instead is you're going to place a short pole, maybe a 1 meter pole. Why? Well, because we can see the shadow of our tree and we can see the shadow of our pole. And these, together with the sun here, give us triangles. Now, because the sun rays are practically parallel, we can prove with F angles and such that these are equal. We know that this is the right angle. So we can prove that these triangles are, in fact, similar. So we can use the rules for similar triangles. Well, let me give the points some letters so we can do it a bit more nicely. We already have something very nice. The triangles are already in the same position, so we don't really have to redraw them. Otherwise, we would start by redrawing them in the same position, so where the equal angles line up. Okay, so we have this. We know this one is 1 meter. That's going to help us out later on. I can't measure my tree, but I can measure the shadow. So suppose this shadow is 2 meters and this shadow is 10 meters. I have no idea about BC or about ST, but it doesn't even matter. What I'm going to do at this point, once I have these triangles, and I want, of course, to get TR, is I'm going to make a table. I'm putting ABC on top. It doesn't matter, it can be the other way around as well. And I fill in my information. I know that AC is 1. I know that AB equals 2. I know that RS, which corresponds to AB, is 10. And I want to know RT. And since they're similar, this has to be a ratio table. So all I have to do is figure out what do I multiply by. In this case, very simple, but if I'd want to calculate it, I divide the bottom by the top, the enlargement by the original, and get a factor of 5. So my tree is 5 meters high. So this is just a small example. I'm not going to go into this any further, or not going to go into more examples. but where we create similar triangles in a way that's going to help us. We can prove that they're similar because we know something about the angles, or in this case about parallel lines. And after we've already proven that they're similar, we still can calculate sides. So this was not possible with quadrilaterals or with any other shape where we had to use all the sides to even check that they were similar. But because we have these very special triangles, we can do this. So in the exercises, you'll get a few examples like this with a real life scenario and just some abstract triangles to practice with this with. Good luck.